Alright, welcome back to part 2 of our lecture about what is turbulence. Now, when last we left, we were admiring good old Lewis Fry Richardson, who tended to do things like write poems and make paintings and stuff about various meteorological phenomena. And his famous poem about eddies and turbulence and so on, said that big whorls have little whorls that feed on their velocity, and little whorls have lesser whorls, and so on to viscosity. What does he mean by all that? Let's actually talk about this in a little slide right here, a couple of diagrams here. I want to consider a situation where I've got some kind of wind shear. Okay, right now, the flow that I'm drawing there looks pretty laminar to me, right? The flow is flowing very smoothly, just slipping past each other. Down near the bottom of the screen, the flow is slower. Near the top of the screen, the flow is stronger. And I don't have any preconceived idea of what it is I've just drawn there. Maybe this is the wind with respect to height, and like the bottom, I've got that grassy surface there, and as I get higher with respect to height, the winds are getting stronger. That might be what I drew. Or maybe like I'm looking down on a map, and this is like horizontal wind shear, where like on maybe that's like the south end of those farm fields, the winds are weaker, and as you get farther to the north, the winds are stronger. There's a wind speed gradient here, or something like that. I'm starting with no preconceived idea as to which way I'm talking about this flow. Nor am I starting with any preconceived idea about what scale I'm talking about. Maybe that arrows that are biggest, and that's the fastest wind, maybe that is 20 meters away, maybe that's 200 meters away, maybe that's 2 kilometers away. I don't really have a sense. I'm over orders of magnitude. I don't care. We're just saying that there's some wind shear here. I'm making no preconceived idea as to how big this feature is. But in this case, the way I have it drawn here, where all these wind vectors are all going from the left side to the right side of the diagram, well, there is sort of a mean flow. Some places the flow is a little faster than this, some places the flow is a little bit weaker than this, but overall there is sort of a mean or average flow, which I'm going to just kind of keep illustrating here with sort of an orange arrow. And that means that the actual flow at each of those locations could be drawn as like how it's different from the mean flow. So like near the top of my diagram there, I have arrows that are going from left to right, meaning the winds were even faster than the mean flow. And then near the middle of that arrow there, the vectors are very small. They're almost the same as the mean flow. And then down near the bottom of that diagram, the vectors are actually in the opposite direction from right to left. And so we are illustrating like the wind is weaker than the mean flow. Okay, so we can kind of think just about this component, the anomaly in the flow, how the flow is different at any given location from the mean flow at that same time. And, okay, but I can still see how it's just sort of a shear. It's just a change in the wind with respect to distance here. And I have a question then. Will the wind really do this? Would the wind really let us have some rather pronounced wind shear like that? Another way to ask it is, I mean, I know wind shear exists, but is it going to really let me have that much wind shear? Well, it's going to depend. It's going to depend on a lot of things. One thing being, I better start deciding whether I mean this is horizontal or if I mean this is like vertical wind shear. So like I'm making this horizontal wind shear again, like the top part of my diagram is north and the bottom part of my diagram is south. And you can kind of see I've got those satellite image of some fields again in the background to illustrate this. So this is horizontally. Well, okay, so like farther to the north my winds are stronger, farther to the south my winds are weaker, and you know, we're talking on the order of like meters to tens of meters to hundreds of meters or something across this region here. There is a certain change in the wind speed u with respect to north-south, in other words, change in delta u, delta y, a change in the wind speed in the y direction. Okay? Well, maybe. Can the wind do this? Maybe. Maybe the change in u with respect to y, in other words, the wind speed gradient here, could be that big. Maybe the flow can still be laminar and do that. And, well, now I've made some adjustment here and I made the wind shear smaller. There's less wind shear here, and we can probably have that much wind shear. I mean, we got a change in u with respect to y, delta u over delta y, that's smaller. Can we have that much wind shear? I don't know, maybe, probably. On the other hand, if we made it really big, like we had lots of wind shear going on between the north end and the south end of this domain, well, probably not. I mean, at some point we would have too much wind shear and we wouldn't be able to have laminar flow anymore. The flow is going to break and it's going to produce turbulent eddies. After a certain amount of wind shear, a certain value of, in this case, change in the u wind with respect to y, it starts becoming easier for the flow to break into a swirl. The easiest way for me to have you picture that is to think of this, like put a pencil or a pen between your two hands and slide them past each other. And you'll see how that pen develops like a rolling motion in between your hands there. Think of it that way. When you have this shear like this, at some point there's enough shear that it's easier for the motion to kind of break into an eddy, to use the right word, a turbulent eddy. So instead of having this broad area of wind shear, we produce a turbulent eddy. Where did that that eddy has kinetic energy. There is actual, there is mass in motion, 1/2 mv squared. There is kinetic energy here in this eddy. Where did it get it? It got it from the mean flow around it. The eddy got its kinetic energy by weakening the mean flow around it. Now, that's pretty slick. But remember, I deliberately told you we weren't making any presupposition as to what size this was. I mean, I could go and forget about those vectors at the top of the bottom of the diagram and just sort of zoom in on the eddy a little bit. And if I zoom in on that eddy, I see that the, let's say, north end of the eddy is moving at it in the opposite direction as the south end of the eddy. That's wind shear. There's wind shear across that eddy. There is a change in u with respect to y, delta u over delta y. In fact, there might even be more wind shear because delta y is getting smaller. We're looking at a smaller area just across this little eddy. You can kind of see where the math is going to start failing us at some point, because as that delta y gets smaller and smaller, we're eventually dividing by basically 0. But, for now, we have wind shear here. That wind shear will not be something that makes the eddy very happy. The eddy will break into multiple smaller eddies. The shear will result in more breaking of that shear down into more but smaller turbulent eddies. And where did they get their kinetic energy from? From the bigger eddy. The bigger eddy will slow down as these little eddies speed up. Of course, where did the bigger eddy get its kinetic energy? From the mean flow. Oh, see how we're passing kinetic energy down smaller and smaller scales of eddies each step of the way. And of course, we could just keep repeating this process as many times as we wanted to, looking at smaller and smaller eddies, and Richardson would come by and say, excuse me, isn't that what my poem just told you? That the bigger whorls have lesser whorls that feed on their velocity? Oh, yeah. Okay. Now, we could keep repeating this process many, many times and just get each of those eddies. Well, the north end and the south end of the eddy are moving in opposite directions. There is shear there. There is a change in u with respect to y. We can also do change in v with respect to x, but we're just doing it change in u with respect to y, which means there's shear, which the flow will not like. The flow will choose to break that down into turbulent eddies, and you'll just keep getting smaller and smaller eddies with time at a time, but there's a limit to how far that can go. There is a limit to how small eddies can get, based on like the viscosity or the thickness of gases and so on in the Earth's atmosphere. At some scale, the flow doesn't produce smaller and smaller eddies. Think about like the smoke rising from a cigarette. I mean, they produce those little swirling motions, and if you watch closely, they may even produce smaller swirling motions on the edges of those swirling motions, but it doesn't keep getting smaller and smaller down to infinity. At some point, those swirling motions stop, and the kinetic energy is transferred into a thermal energy inside the gas itself. At which point Lewis Fry Richardson would step in and say, I'm sorry, was I just talking to myself when I wrote that poem? And lesser whorls have, the big whorls have lesser whorls that feed on their velocity, and little whorls have lesser whorls and so on to viscosity. Right? He had the idea right. He was always doing something crazy like making up a poem or making up a painting about science. What about vertically? like if we had wind shear vertically, again, I got the grass and the sky in the background here, and I'm showing how winds are changing with respect to height. Well, we have a mean wind speed, which I have on that large orange arrow there, and we see that the wind speeds are greater than that near the top of the layer, and they are smaller than that near the bottom of the layer, so there is a change in U with respect to height, delta U, delta Z. And we could ask ourselves, is the flow really going to be able to be laminar and pass over it like that? And, well, it might. We'll have to see what determines whether the flow can be laminar in that situation, but depending on how much wind shear there is, the flow eventually will become turbulent and will break and produce turbulent eddies that originally are on the scale of like the depth of the boundary layer, like, you know, they might be a kilometer or two thick, these swirling motions in the atmosphere. But things are a little bit different in the vertical direction than in the horizontal direction, because in the vertical direction, eddies have components that are about rising motion and sinking motion. See how there's a rising motion like to the left, and there's a sinking motion associated with this eddy to the right? Well, remember, rising and sinking motions are not always such an easy thing in the Earth's atmosphere. Depending on the static stability of the atmosphere, it can be no big deal to lift air parcels or lower air parcels, and they're not resisting their changes in vertical motion. Or if the atmosphere is very statically stable, very stable statically, that can be a lot of work. The atmosphere can really be resisting vertical motions like that. So for example, in this situation I labeled it, well, what if the static stability is very high? This layer is very statically stable. Well, if this layer is very statically stable, we could actually have a whole lot of vertical wind shear between the bottom and the top of the layer. In other words, delta U over delta Z could be very large, but it would still be laminar flow, because it would just be too hard to produce turbulence. That rising motion and the sinking motion associated with each of those turbulent eddies would be so resisted by all that static stability of the atmosphere that we could actually have a huge amount of vertical wind shear and not produce any turbulence. The flow would stay laminar. On the other hand, if, again, I changed the label on the left there, now I'm saying, well, what if we still have that same amount of wind shear, but now static stability is not so high? All right, this air is closer to being statically neutral. Well, then it won't be so hard to produce rising and sinking motions. This wind shear will be able to produce these vertical eddies, and you'll get rising and sinking motion associated with them and so on. So in this layer that was less statically stable, the same amount of wind shear was able to produce turbulence. All right. On the other hand, with that same amount of static stability, you know, we're saying it's not that stable anymore. It's getting closer to being statically neutral. Well, maybe in this case, this much wind shear that I have drawn with these kind of medium-sized arrows here, maybe that much wind shear is able still to produce turbulence, and we get these eddies. The rising motion and the sinking motion can overcome that stability. Maybe. But at some point, of course, no matter what our stability is, there will eventually be a small enough amount of vertical wind shear between the top and the bottom of the layer that we can't overcome the static stability, and we won't be able to produce vertical turbulent eddies, and the flow will stay laminar. This is really nifty, how there's this trade-off here, where we have to think about both. If we're going to be wondering about whether turbulence is going to form, we need to be wondering both about the shear in the environment and the static stability of the environment. How it's going to be resisting any vertical motions that are going to be trying to happen as these turbulent eddies get going. And that Lewis Fry Richardson, he wasn't just a poet and a painter. He also came up with something called the Richardson Number. I suspect he didn't call it the Richardson Number, but that's what we call it after he's been gone. And the Richardson Number is a property of the atmosphere that's going to be telling us something about whether we're going to get turbulence or not, based on a combination of how stable the atmosphere, statically stable the atmosphere is, and how much wind shear is in that layer of the atmosphere. But it's going to be able to tell us that based on a single number called the Richardson Number. The Richardson Number can actually be written lots of different ways. But it is just a dimensionless number, meaning it has no units. And To keep things a little bit simpler, I chose this form. I mean, again, the book I got this stuff from had like 7 different forms for students to derive of the Richardson number. That didn't seem so useful. Here, if I look at this definition, though, the Richardson number, I can see it's a big ratio. It's a big fraction. There's a numerator and a denominator, and the numerator in this form is just the Brunt-Väisälä frequency squared. Now, you might remember the Brunt-Väisälä frequency. Well, that was that business of, like, the actual frequency of oscillations of air parcels that were going over the top of a mountain. That doesn't seem relevant until you remember that another way to interpret the Brunt-Väisälä frequency was it's a measure of stability. It's just going to be bigger the more stable the air is, and it's going to be smaller the less statically stable the atmosphere is. Okay, so the numerator is just a measure of the static stability of the air. Now, in the denominator, there's a bunch of delta U, delta V, delta Z type characters there. The delta Z is going to be the thickness in meters of the layer that we're talking about. And delta U is going to be just the change in the U wind from the top to the bottom of the layer. So you would know the U wind at the top of the layer, the U wind at the bottom of the layer, and so take the difference between them. That's delta U. And we can play the same game with delta V, where V is the south to north component of the flow. So you would know the V component of the flow at the top of the layer and the V component of the flow at the bottom of the layer. Take the difference between them. That's delta V. When you look at that then, there on the bottom, the denominator of this ratio here, do you see how there's like kind of a delta U, delta Z? And there's a delta V, delta Z. It's a little bit of a mess in this particular form to see that this can actually be rearranged and be a way of talking about shear, where it's the change in the wind with respect to height. Okay, again, it's a little bit of a mess to get it. It expands out into a whole mess of terms. But you can kind of see how it's going to have terms in it like delta U over delta Z and delta V over delta Z. And once you have that expanded down there, you can see that this is going to be related to wind shear here. And that gives us our best way to actually think about the Richardson number. The best way to understand the Richardson number is to say it is static stability over shear. It is the ratio of how stable the air is, how statically stable. We're about to come across a different type of stability. How statically stable the air is, divided by how much wind shear there is in the air, how the winds are changing with respect to height. The Richardson number is pretty darn slick. It's going to just be a dimensionless number, and it will be positive most of the time. It's only negative if... no, I'm sorry, I don't think it can possibly be negative. So it's a positive number. If it is a positive number and smaller than, as it happens, 0.25, also known as the critical Richardson number, what's going to happen is that the static stability, the numerator, is small and or the shear is great. So we have the Richardson number, which is the ratio of those terms, is a very small number, smaller than the critical Richardson number of 0.1. And what's going to happen is, well, that static stability is resisting those vertical motions that the turbulence is trying to set up, where there's little bits of rising and little bits of sinking. But there's just apparently so much more shear in the flow that it can overcome that. It can work, it can do the work necessary to lift the air parcel against the static stability. And we're going to get turbulence. This is an important situation in the atmosphere. This is called dynamic instability. It's another use of this word unstable. We're going to say that when the Richardson number is less than 0.25, the flow is dynamically unstable. Remember, we use this word unstable in general to mean like prone to big changes. When the flow is dynamically unstable, that means that it's going to try to quit being laminar and try to produce turbulence. That's different than like statically stable, which is about rising and sinking motion and will the flow resist it or encourage it. When the atmosphere is dynamically unstable, it encourages the formation of turbulence. That's in contrast to if the Richardson number is greater than 0.25, in which we would say that the flow is dynamically stable. There is either so much static stability that we can't really produce the turbulence because we can't get the rising and sinking motions on those eddies, or there is not enough wind shear in the denominator of the fraction to produce the turbulence in the first place. We have another use of the word stability here. In fact, we can make a little diagram here where there's 4 possibilities. where a layer of the atmosphere is either statically stable or statically unstable. And for each of those possibilities, the flow can either be dynamically stable or dynamically unstable. And so you get 4 combinations, 3 of which end up having the same effect. And there are the 3 that I have labeled there in purple. In those 3 situations, turbulence can be produced in either one of 2 ways. Either the flow has to be statically unstable, and thermals are producing the turbulence, because the air parcels are just gladly rising and sinking on their own, or the flow has to be dynamically unstable, where the Richardson number is small, the wind shear is more than enough to overcome whatever static stability there is, and we produce the turbulence despite the static stability. So 3 of these combinations, the ones in which it's either statically or dynamically unstable, we get turbulent flow. That means there's only one possibility where we get laminar flow. If you're going to get laminar flow, you have to have an environment that is both statically stable and dynamically stable. It has to be statically stable, fighting the vertical motions due to this temperature structure of the layer, and it has to be dynamically stable. There can't be all that much wind shear. But as long as you meet those criteria, the flow will be laminar. If you don't meet those criteria, whether it's because you were statically unstable or because your layer was dynamically unstable or your layer was statically unstable, you'll get turbulent flow. We're going to see a bunch more examples of this and what it all means and so on, but let's ask a couple quick questions about what you just saw. Question 4. Suppose that the flow is laminar, and yet it has a lot of wind shear. You measured it or whatever. From this information, we know that the layer of the atmosphere must be A, statically unstable, B, statically neutral, C, statically stable, or D, dynamically unstable. Only one of those is something that must be a consequence of what you observe in that problem there. The flow is laminar, but with a lot of shear. Which of those has to be the case? Make a choice from those 4 options and get a little feedback before you move on to question 5.